Hi, today I wanted to talk about real-time pathfinding and how I managed to get 120 characters to find paths in real time whilst avoiding dynamic and static objects and at the same time avoiding each other. So, first of all, why is this necessary? Well, to consider that, I need to give you a little bit of a background on We Could Be Heroes. So, let's start off with how I initially approached this issue. At first I thought, well, most of the stages, they're not going to have over 50 characters attacking you at the same time or anything like that. You're mainly going to be attacking smaller groups because obviously it's a beat 'em up. So in the initial stages, you may get 5 to 10 characters simultaneously attacking you, and in true beat 'em up style, each character kind of takes it in turns to attack your character, so they won't all group up on you and simultaneously start beating you. Each one will kind of find a position to surround you, and then they'll take it in turns, one at a time, to attack you. The minute you hit an enemy though, the next enemy begins trying to attack you from an alternative position or a different angle or whatever. So at that point, the pathfinding becomes important to happen as fast as possible. Now initially I thought maybe we could wait kind of, a fifth of a second, something along those lines, and do pathfinding at every fifth of a second. And to be honest, this worked kind of great when you had smaller groups of 5 or 6 enemies at a time. What would tend to happen is a character would come to attack you, you'd hit that character, and within a split second the next character would start to attack you, and we wouldn't really notice a fifth of a second delay on that character coming to attack you. So what's the problem? Well, in We Could Be Heroes, you're kind of free to move about anywhere on the stage. You're not locked to a particular screen where you have to defeat those enemies and then move on to the next group. You are locked to a stage zone, but that zone could include up to 50 enemies, and it's up to the player to decide how they want to engage those enemies. They may walk in and start attacking the first 5, or they may literally run around the whole stage with all the enemies chasing them and end up with 50 players all simultaneously attacking them. Now, when that occurs, the issue would be pathfinding only occurring once every fifth of a second. Eventually, those paths would build up quite a queue log. So you would have 50 characters. Technically, the latter side of those characters, they would be finding a path every 10 seconds. Now, obviously, there is another side to that you'd think, well, why is that a problem? You could potentially prioritise the ones that are close to your character, and it surely shouldn't be too much of an issue. Well, the problem is that those paths would queue up. You'd end up with somewhat having to wait 10 seconds. If you, say for example, flying kicked one of those enemies that was waiting, their path would still be queued, and so you'd end up with queues building on top of each other. Eventually, this queue would grow to longer than 10 seconds, it could be 20 seconds. Now, you could cancel previous tasks that the characters had done, that'd be fine, but you'd still end up with this issue where, essentially, some paths would take longer. And no matter how you look at it, those paths, if you start chipping away at them and you manage to get that down to a 1 second delay by somehow speeding up the paths, well, you've still got the issue that if you see an enemy that's standing there waiting to attack you and you're dodging the other characters, you go and attack that enemy and he's still waiting for his path info. It kind of looks sloppy. So, how did I solve this issue? My initial thoughts were, why don't I just multi-thread it? Problem solved, and all I'll do is shove all the pathfinding onto a separate thread, and that thread can be called out to perform the pathfinding and return the result once the path has come back. Now, this kind of worked, and it did have reasonably good results, but again, once we started getting a massive amount of enemies, it started having 2 issues. First of all, if you ran a long way away from the enemies and left one enemy downed somewhere on the map, then that enemy would take longer to calculate its path to get to you. So because that path would then take longer than the other paths, it would hold up the decision making for all the other characters. And even if this ended up only being half a second, that delay is very noticeable. So that issue was kind of out of the window, and I started stumbling across, well, what I really need to do is do all of the pathfinding for all the characters across as many threads as I can every frame. That way, if your main player moves, then the characters will immediately change direction and immediately follow your character. Maybe if you manage to move one of the dynamic objects, like a bin, you throw out another enemy, that bin then ends up in the way. Those players can then, the enemy characters, can then make a decision to move around that bin rather than walk straight through it because their previous path told them to. So, how on earth did I manage to achieve this and get it fast enough? Well, let's talk about that. So initially I started working with Unity jobs and the IJobParallelFor, which performed fantastically to a certain extent. The issue was that ultimately all of those paths together ran at around about 120 milliseconds in the worst case scenario, which is where I had long paths for the characters to calculate or complicated paths. Now, a total of 120 milliseconds is quite a long time. Not so long once you start splitting it across multiple threads, but not every machine has got multiple threads. So we'll have to start considering machines that have only got maybe 3 threads spare. And on those machines, we need this to run a hell of a lot faster. So, I started by optimizing my pathfinding algorithm. And the first optimization was to place some markers within the burst compilation code and to profile it using the Unity profiler and see where the slowdowns within it were. So initially I was using native lists to insert the nodes that I was searching through using a classic A-star pathfinding algorithm. Now mine's slightly customized because I do real-time calculate where objects are within the game that have moved, like bins and other characters. So it's quite bespoke to my problem within my game. I also store whether or not characters can jump over certain things like tables and things like that. So obstacles can sometimes be jumped by the enemies, and I store kind of like whether or not they should do that. And I also store obstacles like roads that may have a car on it that may run over an enemy. So those elements are all stored, hazards and things like that the NPCs need to be aware of. So the issue with using the native list seemed to come around by finding the index each time that the previous nodes were stored at in order to remove or add them to each path. So A-star is quite a simple algorithm, and you have a closed set and an open set. The open set is essentially a flood fill of the entire stage environment geared towards the target. And then the closed set looks at the values within the open set and takes the most applicable value. In order to do this, you loop through the open set each time, evaluate the results, and then remove the node from the open set and add it back to the closed set. Now, I found most of the slowdown to be caused by adding and removing these nodes because of the fact that you needed to look up the index, and when you're potentially talking about 1024 nodes with a long complicated path, that can become quite time consuming, particularly as you're generally doing around about, for each neighbour, including the diagonals, 8 times that anyway, and then continuously repeating that over a long path. So initially I thought, well, Unity has a native hash set which is specifically designed for storing indexes. This must be the fastest solution compared to, say, for example, using a native list. So initially I inserted that and found the results to be quite dissatisfying. It dropped the performance down to around about 80 milliseconds rather than the 120 milliseconds I originally had, but it didn't improve the performance that great, and sometimes the performance would still drop down to around about the 120 millisecond mark. Not quite as slow as the native list, but not significantly better. So my initial thoughts then turned to, what if I cached all the neighbours and what their node indexes were, and also cached all of the things like, for example, whether or not there was a thing like a bin or something like that that needed to be avoided. And I pre-calculated all of those values for every node within the grid. Doing that dropped the speed down again a little bit, and I was saving a few milliseconds here and there. But overall, it was still the inserting and removing of these node indexes that were causing the slowdown. So I needed a better way of dealing with those. And in the end, I came up with a solution which revolved around ditching the native hash set and turning back to a list. So here's what I did. I created a separate native array that stored the data that was modified to determine how efficient the path was. So rather than storing that alongside the nodes, I created another set of another native array that was the same length and just stored that data. So that array stored the G cost, the H cost, the calculated F cost, what the parent node was, and more importantly, what the index was within the open set. So by doing that, I no longer had to find out what the index was for the node within the open set in order to remove it. I could just use the remove at function from within the native list. And I no longer had to do a contains to find out whether or not a value was stored within the open set or not. All I simply did was set the index of that node to -1 within the index for the open set. So if that value was greater than 0, greater or inclusive of 0, I would know that that node was within the open set and what index it was at instantly. This completely changed everything. My performance went down to a few milliseconds. In fact, in most cases, the performance is around about 0.05 milliseconds, which is phenomenal. And for the total group, you're talking maybe 0.2, 0.5 milliseconds for the entire group, taking into account that this is all running on a separate thread, so it doesn't even affect the main thread at all anyway, but it leaves plenty of room for my other multi-threading that I use within the game. So let's have a look at the pathfinding happening in real time. So here you can see Simon running around outside of the supermarket, which is shown on the left hand side of the screen at the bottom there. And you can see the paths are clearly finding their route around the subway there, and then the short route throughout the inside of the shop through the doorways. And this is all because some of the routes will be cut off because there are too many enemy players blocking the path. That total takes about 0.3 milliseconds there, total of 1 millisecond. And here we can see that we've got a whole bunch of enemies. This is running a little bit slower because we've got 50 enemies running within this scene, all using dynamic pathfinding around this huge amount of bins that I've chucked into the scene. The slowdown's actually because of the physics within the scene and not because of the actual characters themselves. So let's have another look at them running around. These areas here are all breakable shelves, so at any point those could be destroyed, but as you can see the enemies avoid those shelves and jump over little gaps that they find. And again, as you can see, we're looking at a maximum time of just under 3 milliseconds in total. Again, I've limited this to 3 worker threads to simulate a slower machine like a laptop or something like that will give you a limited amount of resources. And here we can see a breakdown of every thread that's every single job that is required to create the pathfinding, including the ones that block off the paths. Let's have a look at 120 enemies. So again, running a little bit slower. This slowdown unit is internal physics and various other things that are occurring whilst the pathfinding is going on. But despite the fact that this does run a little bit slow, you can see the pathfinding churning away there in real time and working fantastically. The characters, if you look in the middle here where my mouse is, you can see that they're alternating their paths depending on those shelves being in the way, but they're also slowing down so that they don't overcrowd and get in the way of other NPC players, which is quite important, because whilst I don't mind the NPCs getting slightly over each other and crowding up on each other, sometimes even occupying the same space if necessary, ideally I want them to group up like this and look like more of a crowd than just being bunched on top of each other. So let's have a look at the pathfinder of this, and as you can see, even with that many agents, you're only looking at about 3.44 milliseconds in total, which, considering that there's 120 characters there all moving, it's quite phenomenal, I think. And again, only using 3 worker threads compared to the normal 14 that I would have on my machine. Is a breakdown of those jobs on that single worker thread. You can see clearly on the graph here the amount of time that is being taken up by the physics processing, which is a lot down to the fact that every character acts as an active ragdoll, so that when they're knocked over they can turn into a ragdoll, but at the same time they can interact with environmental things like cloths and things like that. So overall I'd say this worked out very well. One last thing I'd like to show you is what happens when if we freeze the paths and still leave them running in real time, but now we walk Simon around and you see this little grey area around him followed by a pink area. That grey area and pink area represent the area that we don't want the NPCs to really go into unless they have to. And this means that, you know, when an enemy approaches you to attack you, we ideally don't want them to kind of glitch in at you from funny angles. Something that you find some of the beat-em-ups do as a way of cheating the difficulty in the game and making it more of a kind of cheeky little move that the enemies do. I ideally want to avoid that. I want the enemies approaching you from either side continuously as fast as possible, so that it makes the action more dynamic and becomes more about how you manage the enemies as opposed to them using little cheat tactics to defeat you. So you can see as I walk through the paths here, the paths automatically divert around to those grey areas, only going into the pink areas if absolutely necessary. And the dark pink dot in the middle of my character kind of represents a no-go area. That's where the enemies don't want to go according to the pathfinding. They can go there if they want to grab you or something like that. Anyway, I hope you found something useful within this discussion. Overall, the code and the optimization took me about 2 hours to write in total. In fact, this video took me 4 hours to create, so a lot longer than the code. If you have any questions, ask below and I'll do my best to answer as soon as possible. Anyway, bye for now, and don't forget to check out We Could Be Heroes on Steam.